So yesterday we kind of introduced this idea of the work energy theorem. Okay, so just as a quick review here, work is a change in mechanical energy. For us in Science 10, that's going to mean either a change in potential energy or a change in kinetic energy, but never both. Okay? In reality, when work is done, both types of energy, potential and kinetic, can change because when you add them together, that makes mechanical energy. Okay? So the sum of something's kinetic and potential is its mechanical. But we just, for the sake of keeping it a little more simple in grade 10, we don't do problems where both change. So one of your big challenges when you're reading a work energy theorem problem is to determine which of the two energy types is changing, kinetic or potential. Okay? So kinetic energy is based on mass and speed. Okay? We talked about that yesterday when I went into my little rant about why you shouldn't speed through a playground zone. Okay? So if a question has a situation where the speed of the object is changing, then that means the kinetic energy of the object is changing in that question. So whatever work is being done is causing the object to go faster or slower, and thus change its kinetic energy. If an object is lifted in a question, so they mentioned something about a change in height, okay? Either it's falling or it's being lifted up, then there's a change in potential energy, and the work being done is changing that. Okay? So your challenge is to read through a question and figure out which one first. Okay? So work's this change in mechanical energy, either potential or kinetic. And the amount of work done can be calculated by multiplying the force exerted by the distance over which it is exerted. Okay? So the harder you push or pull, the more work you can do. The farther you push or pull, the more work you can do. Okay? Everyone all right with that relationship? Making sense from yesterday? Okay. So in this question, a tractor pushes a rock, and we're told the mass of the rock. So one of our givens here is the mass of the rock, 550 kilograms. From rest to a speed of 4 meters per second. Okay, so my VI is 0 meters per second, and my VF is 4 meters per second. What kind of energy is the work changing? Kinetic. It mentions that the speed changes. It has no mention of the height changing. The tractor is not lifting the rock, it's rolling it along the ground or pushing it or whatever. Okay? It's doing something with it, but it's not going any higher or any lower. It's just going faster. Okay? So right away, we can write that the work in this question is changing the kinetic energy of the rock. Okay? And you would get a mark for that. Okay? The last given we have is the distance that the tractor pushes the rock, and that's 25 meters. Okay? And obviously you get a mark for your givens, just like always. All right, so my next step here is that now that I know what kind of energy is changing, and I know what my givens are, I need to take this formula, W equals delta EK, okay, so work equals the change in kinetic energy, and I need to expand it out. This is the short form. Okay? The long form of this formula looks like this. Work is calculated by multiplying force times distance. Okay? And change in kinetic energy means subtract the initial from the final. It's the way we calculate all change. Okay? It's always final minus initial. So basically I'm saying 1/2 mvf squared minus 1/2 mvi squared, because this is the formula for kinetic energy, and I'm indicating that one of them is the initial and one of them is the final. So you would likely get a mark for that expansion as well. Okay, what does the question, what part of that formula does the question want me to solve for? force. Yeah. Wants me to solve for force. Which one of the letters stands for force? F. Yeah. Okay, so I'm looking for, and I probably should have written that over here in my givens, I'm looking for force. All right. I want to get force by itself. Lucky for me, that means I only have to move one thing. What is it? D. How do I move D to the other side? Divide. I do the opposite. All right, so I'm going to divide both sides by D. Now, I'm also lucky in that I can simplify that side a little bit. What was my initial velocity? 0. So, what's 1/2 times m times 0 squared? Right. Okay, so I've got my formula. Now all I have to do is plug in my numbers. Okay, so F equals 1/2 times 550 kilograms times 4 squared, okay, divided by 25 meters. Okay, so that will calculate the force the tractor exerts on the rock. Okay, so this is like a very small toy tractor because that's an incredibly small amount of force. But this would also assume that it's frictionless, and so you wouldn't have to work very hard to push a big rock like that. Okay, so 176 newtons would be my answer. Okay, so a work energy theorem problem is going to ask you to calculate force, or it could ask you to calculate distance, or it could ask you to calculate one of the speeds, initial or final. Okay? If this was a question about potential energy, it could be force, it could be distance, or it could be height. Okay? One of the heights, initial or final. That's the question.
How do you know if it's newtons or joules?
Oh, because force is in newtons and work is in joules. Energy is in joules. So force and work are different. Okay? Force is how hard you push or pull. Work is how much you change energy by. Okay, does that make sense? That's a good question because that often comes up. I often see people write joules in the wrong place and newtons in the wrong place. So newtons are the units for F. Okay? Joules are the units for work or for energy. They're not the same thing. All right, questions on that one? Okay, now here's the good news. Every work energy theorem question follows the same pattern. The only thing that will be different is some will ask you to solve for F, some for D, some for V, some for H. Okay, but the setup to get to that point is always going to be the same. Okay. I want you to write this one down, and then we're going to walk through it. This one's a little bit different. Same pattern, but a little tiny bit different. Okay? So if we're writing down our givens for this question, okay, the first given we have is that the mail carrier picks up a 10 kilogram package. What did they give me? Mass. Okay, and they're on the 3rd floor of a building that's 30 meters above the ground. And they deliver it to the 10th floor that's 100 meters above the ground. So they just gave me two different what? Well, actually not V, because that would be meters per second. These are heights. Okay, 30 meters above the ground, 100 meters above the ground. Okay, so we're looking at initial height, 30 meters, final height, 100 meters. Okay, and they're asking for how much work is done. This is actually going to be easier than our last question, because I'm not given force or distance here. I'm just asked to calculate work, which means less work, actually. Okay, so what kind of energy is being changed in this question? Mechanical. Specifically, what part of mechanical? Kinetic or potential? Potential, right. Okay, so both of those answers are correct. Okay, if you change the potential, you change the mechanical. If you change the kinetic, you change the mechanical because they add up to it. Okay, so work is going to change the potential energy in this question. Okay, now I don't have to write out the formula force times distance for work because they don't want that. They just want the work. And work is the change in potential energy. So that's going to look like this. My final potential energy minus my initial potential energy, right? Because that's what delta means. It'll be potential final minus potential initial. Okay, do I have all of those numbers? I have mass, I have the two heights, and what is G always? 9.81, right? So I have all the numbers here. I can calculate the work just by plugging in the numbers into my formula. The hardest part of this question was determining, was it potential or kinetic that was changing? So this will be 10 times 9.81 times 100, that was my final height, okay, minus 10 times 9.81 times 30, the initial height. That's going to require 6,867 joules worth of work. Okay, how did I know the units were joules? Because it's work, yeah, and it's potential energy. It's the change in potential energy. Kilograms times meters per second squared times meters, kilogram meters squared per second squared, joules. Okay? Everybody okay with that one? Okay. Did we follow a very similar pattern on that one to the last one? We wrote out our givens. We identified the type of energy being changed. We set that equal to work, and we solved. Okay. In the last question, we did all of those things. We set it equal to work, and then we had to manipulate the formula for work. It had an extra step. Okay. This one had less to do. Okay, I want you guys to try this one on your own. The answer is there, so you can check it when you're done, and then we'll walk through it together. So a bulldozer does 7,500 joules worth of work in pushing a truck from a speed of 2 meters per second to an unknown velocity. If the truck has a mass of 2,500 kilograms, what is its final velocity? Okay, in this question, okay, what are our givens? VI. What else? Work. And mass. Okay. What are we looking for? VF. Okay. So what kind of energy is changing in this question? Kinetic. Yeah, change in speed. So the work is changing the kinetic energy of the truck. Okay, so that's going to mean work equals, and notice I'm not putting in the force times distance because I was given neither and asked for neither. I was told, here's the amount of work, so I have that number. Okay, equals 1/2 mvf squared minus 1/2 mvi squared. Okay, so I want to get vf by itself. What should I do with this entire term right now? It might be easier to see it if I wrote it like this. What should I do with that term right now? Add it to the other side. Exactly. Work's a change in energy. If I add the change in energy to the initial energy, which is what I'm about to do, that should give me the final energy. Agreed? Okay, so what I'm going to be left with here is this. Work plus 1/2 mvi squared equals 1/2 mvf squared. Okay, so all I did was take the initial kinetic energy and move it to the other side. That'll help me to isolate the final velocity, vf. So how do I get vf by itself now? Divided by half of m. Okay, that gets me vf squared. What do I want? Vf. So what do I have to do? The whole thing. Square root it. Okay, that's the trickiest manipulation you'll ever have to do with this formula. Okay? And it's a lot, I'll give you that. It's a lot. Okay? It's a lot of algebra. So when we plug in our numbers, okay, we're going to have 7,500 joules, that was the amount of work, plus 1/2 times 2,500 kilograms times 2 squared divided by 1/2 times 2,500. Okay, I should get 3.16, but we'll double check. 7,500 minus 0.5 times 2,500 times 4. Okay, divide that by 0.5 times 2,500. Oops, that's got to be in brackets. See, it's easy to forget that bracket stuff. Okay, and then I take the square root of that. Oh, I messed up somewhere. I subtracted. That's where I messed up. I subtracted. Okay, so let's do that again. 7,500 plus 0.5 times 2,500 times 4. Okay, that's better. Okay, now I'm going to divide that by 0.5 times 2,500. And then I'm going to take the square root of that. 3.16 meters per second. Okay, like I said, that's the trickiest. I have never put one that difficult on a unit exam. I've put one like that on a unit exam, but I didn't have any initial velocity. So your initial kinetic energy was 0, which eliminates a lot of your algebra. Okay, still the same idea. Okay. If this is intimidating you, you're probably not alone. Okay? It does take a little while to get the hang of this work energy theorem stuff. That's why we spend so much time on it. Okay, so here's the steps for any work energy theorem problem. Okay? First, obviously, write out your givens. Okay? And know that work is a change in energy. Okay? At this point, you need to identify the type of energy being changed. Is it potential, mgh, or is it kinetic, 1/2 mv squared? Okay, your second step is to set up the work energy theorem. So work equals the change in whatever type of energy is changing. Force times distance, okay, is final minus initial. And if it's kinetic, it looks like this. And if it's potential, it looks like this. And then your last step is to manipulate and solve for whatever the question asks you to solve for. Okay, before I go into any more, I'm gonna give you a 5-minute break here. Okay, because you guys have been working pretty hard here the whole class so far. So I'll give you a 5-minute break, and then we're gonna continue to work on these work energy theorem things, just so you see a lot of examples, okay? So you have a lot of experience to draw from. Okay, so this one's relatively easy, but there's one small trick. The small trick is that one of the numbers you're given is going to be used twice in the formula. It will be two things in the formula. Okay, that's kind of the little trick with this one. All right, so write it down, give it a try. Look at this one, because this does have a little trick. Okay, now the things I'm given. First off, the force is unknown. I'm being asked to calculate the force. Okay, it gives me the mass, 50 kilograms, and then it says it's lifted to a height of 1.5 meters. Okay, so that's our initial height is 0, and our final height is 1.5 meters. Over what distance do you exert this force? 1.5 meters. That's the thing that gets used twice. In any potential energy problem, the height, the change in height, and the distance over which you exert the force are the same. They have to be, otherwise how would you lift it? Okay, you have to exert the force over the same distance you lift the object. Okay, so that's just something to watch out for, because it actually happens quite often. All right, so here's what we're left with then. Work is a change in potential energy, because this question is talking about lifting and changing height and things like that. Okay, so we're going to have then force times distance equals m times g times hf minus m times g times hi. But what is m times g times hi? 0, because we weren't told this explicitly, but we have to assume it. It was lifted to a height of 1.5 meters. Where's height measured from? The ground, where the height is 0. Okay, so it's just one of those things that we have to kind of recognize intuitively. Okay, if they don't expressly say something like the initial height was 0 or it was on the ground, but they say height's measured from the ground. I don't know where else we measure height from. Okay, so this is my formula. I'm just trying to find force. Now, what do I have to do with D? Divide it over to the other side. Are D and HF the same number? Yes. Then they cancel. You don't have to cancel them. You can put them into your calculator. It'll cancel them for you. Right? But they cancel. They're the same number. So the force is equal to m times g, which, we haven't gone over this yet, makes perfect sense, because when you multiply m times g, you are calculating the force of gravity, which is the exact force you would have to exert in order to lift something. You have to exert a force in the opposite direction to gravity. Okay? So when I do this, I'm going to have 50 kilograms times 9.81, which is going to give me 490.5 newtons. Okay, so that's a mathematically very simple question, but there's tricks to getting to the math. And that's always the challenge with physics. Okay? I don't claim to be a particularly strong mathematician. Okay? I'm not. But I can do physics very well. My knowledge of physics can help me get to the math. But oftentimes, I actually have very strong math students take physics because they figure physics will be easy for them, and they struggle because they just want to do the math, and they don't get the physics that gets them to the math. Okay, what we're looking at here is the physics that gets me to the math. Understanding that there's a change in potential energy, and that this force is causing it, and so on and so on. Being able to see the physics is important, because none of the math we do in high school physics is extraordinarily hard. Okay? Most of it is just basic algebra. Getting to the math is the challenge. Okay? I often have students in Physics 20 who are not very good at math, or they think they're not, but they're just fine at it. okay? But they understand physics very, very well, and they often do the best. Okay? So if you're thinking, I'm gonna be terrible at physics because I suck at math, you're completely wrong. On two fronts, you probably don't suck at math, and you don't have to be good at math to do physics. At least high school physics. When you start getting into like nonlinear physics in university, you gotta be good at math, but, okay. Which is why I didn't take any of that stuff. All right, questions on that one? Okay. All right. We talked about this going up a hill thing yesterday. So see if you can give this one a try. I will tell you that the speed of the block is not changing. Okay? It is going up the ramp at a constant speed. So okay, that can hopefully help you. So our givens are that we know the mass of the box, 35 kilograms. We know the initial height of the box. What's the initial height of the box? 0. It's at the bottom of the hill. Okay, so 0 meters. And we're looking for the final height of the box. And we know the distance over which it's pushed is 25 meters, the length of the hill. And we know the force used, 150 newtons. Okay, everybody with me there? All right, so what kind of energy is being changed in this question? Potential. We're changing the height of the box by pushing it up a ramp. Okay, so work equals the change in potential energy. Expand that out, force times distance equals m times g times h final. And I'm not even going to bother writing m times g times h initial because it's 0. Okay, and so now I can figure out the final height. What do I have to do with m and g? Divide it over to the other side. Hey, plug in my numbers. I got 150 times 25. So force times distance divided by 35 times 9.81. Okay, so it's going to be 10.9 meters higher at the top of the ramp. Okay, this starting to make a little more sense? They're very patterned. If you can learn the pattern, you can do these. Okay? Okay, we will see you guys tomorrow. Remember, your acceleration labs are coming up due here, so make sure you're working on those.